So GPS is a solution, but not everywhere, as I think we've highlighted. To quote one of the chief scientists from one of the equipment vendors, he likes to say GPS is free and it works, but that's okay. He's a North American, so he's allowed to have that view, but it's still, as we've seen earlier, it's not suitable for every installation. And as Chris quite rightly pointed out, we need to consider the installation. Specifically now, if we're talking about different parts of the network, disparate parts of the network, all being aligned to the same tick, the same 1 PPS tick. The delay through cables, the delay through splitters, the delay through amplifiers, it all becomes significant, whereas in a frequency-only network, that wasn't necessarily the case. So it's just making the point, making you aware that for phase alignment, then we need to really consider calibrating, measuring that, and installing GPS in a more thoughtful way. Certainly for small cells, for femto cells, the residential installation, usually the sort of quote that comes out is, you have a residential user with a zero-touch installation that wants to put the box in the cupboard under the stairs or on top of the radiator, so it certainly has difficulty seeing GPS, getting GPS reception in those locations. Using the EE definition of some of the small cells, it's an outdoor cell in the urban clutter. So when we talk about urban clutter, what we're talking about, is street lamps, street furniture, the sides of buildings. So it's in those dense urban environments. And of course, we have to consider interference. So I think these guys here are some sort of military GPS jammers doing some exercises. We've talked about this a little bit, but still have to consider that. There are documented stories of you might not consider that military jamming is going to affect civilian operations, but there are documented stories of military jamming ships sailing into harbour with jammers inadvertently turned on and taking out whole areas of GPS service. And of course, there are the handheld so-called privacy jammers, things like this, that people think they are taking out cell phones to try and to stop people being disturbed in environments like this. We could be jamming cell phones now to stop them ringing, or people in theatres or in cinemas. And what they buy from the internet is something like this that doesn't only jam Wi-Fi and cell phones, it also jams GPS. So it's not always intentional, but it is there. It is a problem. So this is the urban clutter. This is the EE definition of urban clutter that we were talking about before. Install GPS on the lamppost? Maybe not. We're talking about a very small physical footprint for a GPS receiver, or on the side of a building somewhere. We have limited sky view. We have all sorts of other things going on. So GPS is certainly a part of the solution, but it's how you manage it, how you distribute that through the network. So the typical scenario would be GPS would be in a properly installed central office type location, and then distribute that GPS quality, that GPS timing distributed over the network. This is an excerpt that I copied and pasted from an HP paper from 1996. So bear that in mind. It's nearly 20 years old, and it talks about timing errors within GPS systems. So there's some specification here for the GPS system itself at 95% probability. So if we ignore that for now and think that if we hope that GPS has got a lot better, the figures down here haven't changed. So some of these figures talk about delay variation through the ionosphere and the troposphere and their effect on GPS receivers. So they're talking about tens of nanoseconds. Solar flares, Charles mentioned space weather. So depending on the level of the activity, depending on where the Earth's orbit is relative to the sun and how much of those charged particles the Earth sails through, we can cause, again, tens of nanoseconds to complete system, the GPS system that is being inoperative. The user segment, so this is the receiver. Again, we're talking possible accuracy issues in the way the receiver's designed. Antenna, we talked about the 3 nanoseconds per meter. So that's 3 of those rulers, a nanosecond per foot, roughly. Multipath, environmental. So we're, again, tens of nanoseconds. The point I wanted to make with this slide is going back again, once again, to Martin's 500 nanoseconds. If we're talking about possible errors and uncertainties within GPS of these sorts of magnitude, then you can see we're quickly eating into that budget. If we get 100, 150, a couple of hundred nanoseconds, and we need to then provide 500 nanoseconds at the edge of the network, we are eating into that budget. So that's not to say that it isn't doable. And again, bear in mind, this is from 1996. And this is GPS, not necessarily made for a telecom application. This is GPS as it stands. As we said, you can tie a GPS receiver with a rubidium oscillator that will filter out some of these longer term changes in some of these. But I just really wanted to make the point that, you know, we're almost on the limit. We're talking about 500 nanoseconds or even lower. Some of the figures that have come out of liaisons with the ITU are going below that. So I just wanted to make that point. And again, this photo rather seems to have been shown once or twice this morning. I think Mr. Roberts had it in his presentation. This is an installation where the customer complained that the GPS system was fine during the night, but it wasn't working during the day. And so when they actually got to the bottom of what was going on, obviously this is an office-based environment. The air conditioning is on during the day, off during the night. So there's just enough radio interference to knock out the GPS signal. So again, emphasizing those points.